Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking on the paper machine learning. As we have been talking in the previous two modules, we had spoken about Markov model, the basics of a hidden Markov model, and then we had spoken about three issues associated with HMM, and we had discussed two issues or problems in the previous module. Here we are going to talk about the third issue or problem or whatever you want to call it, which is solved using expectation maximization. So, these are the people responsible for the development of this particular module. So, let us look at the list of objectives again to understand the concept of model learning. So, actually here we are learning the model. Okay. In the previous two modules we assumed that the initial probability, the state transition or the transition probability and the emission probability was given to you. Here we are wanting to learn those probabilities, and we are going to look at how expectation maximization, which we have already seen, the basics of which we have seen in the previous module, some of the previous module, is used for these estimation of these parameters. And we are going to understand parameters estimation. We can use supervised and unsupervised, but basically we will be talking a little more about unsupervised technique. So, the keywords here are hidden Markov, parameter estimation and expectation and maximization. So, just for a quick recap, this is HMM formalism. So, you have a set of states and you have a set of observations. The observations are output, you can actually see the set of states are hidden states. So, here in this particular diagram you are given S, K, S is a set of states, K is a set of observation K or V, and then you have the pi A B, pi is the initial probability, A is the transition probability and B is the emission probability. Now, so this obviously pi is equal to the initial state probability, state transition probability and the observation state probability or emission probability, both our terms are used. Now again, remember in the previous module we have solved the two problems: evaluation, computing the probability of a given observation sequence. What is the probability that observation sequence can come in that way? Sequence, remember, it is a sequence problem. Second is decoding, given an observation sequence, what is the probability of that particular, the probability of the most likely hidden state sequence. Now we are going to the problem 3, which is learning, given an observation sequence and a set of possible models, how do we select the best model that fits the data? Okay, so that is the one we are going to tackle in this module. So again we are just repeating the previous what we said in the previous module. How do we adjust the model parameters? The model parameters are the transition probabilities, the emission probabilities and the initial probabilities, so that we can maximize the probability of seeing that particular observation sequence given the model lambda. So learn the best model given the observation. So here we are going to use the expectation maximization heuristic. So this problem, of all the three problems, this is considered to be the hardest problem to solve. So, you are given the observation and a class of models, each of the form ABP, which specific model best explains this particular observation. A solution to question 1, that is the one question, efficient computation of the probability that a specific model M produces that particular observation sequence. So, this can also, the same problem can be used as can be viewed as a learning problem. We want to use the sequence of observation in order to train an HMM and learn the optimal underlying model parameters, which is the transition output probabilities. So, how can we estimate the emission and transition probabilities given observation, and assuming that we are bringing a new parameter, assuming that hidden states are observable during the learning process. So, we have both the observation and the hidden states. How can we estimate emission and transition probabilities given only the observation? So, these are the two issues. So, up to now we have assumed that we know the underlying model. Okay. Often these parameters are estimated or annotated training data, which is what is supervised learning, which has two drawbacks. Annotation is difficult and very expensive. It is difficult in the sense that it requires a lot of manpower, and it can be ambiguous also, and training data that we used for training could be completely different from what we are seeing now. So, it is better to have a learning that is unsupervised. So, we want to maximize the parameters with respect to the current data. We are looking for a new model lambda dash such that lambda dash gives me the best probability, the maximum probability that this observation will be seen given the model. So, what we are changing at the model? You keep changing the model such that the probability of the observation given the model becomes the largest. This is the argument max problem, which we also saw in Vertebi. In Vertebi, what we did was we tried to find out the best sequence Qs. Given the observation, we tried to find out the best state sequence. Here, given the we are trying to find a model, the other way around. Given the model, we have the observation. We are trying to find the best model, maximum probability of the best model. So, we are going to the parameter estimation problem. So, what we do is, as in any problem, we make an initial guess for the transition probability and the emission probability. Then you compute probability one hidden state follows another and the sequence of observations, which we can do using the forward backward algorithm we have already discussed. Now, compute probability of the observed state given the hidden state, probability of one hidden state following another. So, state sequence, and then the probability of an observation given the hidden state and the sequence of observation. So, again you can compute this using the forward backward algorithm. Then use these computed probabilities to make an improved guess. Now, you start an initial guess, now you try to improve, you are given these. So, try to improve Aij and Bk. Repeat this process until there is no more change in the transition probability and the emission probability. Now, can be shown that this algorithm does in fact converge to the correct choice for the transition probability and the emission probability, but the initial guess should have been close enough. Then we keep doing this. So, what we are doing is, we are given an initial, we are assuming an initial transition probability and an emission probability. We are not too much bothered about the initial probability at the time moment, and then we are trying to find that the probability that this hidden sequence follows another given the sequence of observations, and we are also trying to find out the probability that what is this observation given that this state occurred and the sequence of observations there. So, both can be found out using forward backward algorithm. Once this is done, use these values to make a improved guess for the values. So, given an observation sequence, find a model that is most likely to produce a sequence. It is not an analytic method. Given a model and observation sequence, you keep updating the model parameters to best fit the observations. So, let us just take a look at the review of the probabilities that we were dealing with. One is the forward probability, the probability of being in state Si given the partial sequence observation O1 to OT. Backward probability, the probability of being in state Si given the partial observation OT plus 1 to T. Okay. Transition probability eta t I comma j, the probability of going from state Si to state j given the complete observation 0 1 to 0 t, and the state probability gamma t I, probability of being state I given the complete observation 0 1 to 0 t. So, we are given the observation, have all the probabilities, that is the forward probability, the backward probability, the transition probability and the state probability we are defining. So, forward and backward probability, transition probability and the state. So, what we are trying to do is, given the probability of traversing an arc from I to j is nothing but the probability of the forward probability of being in that state at time t, the forward probability the transition probability of going from I to j, the probability of observing at j observing O at time t plus 1, and the beta j of t plus 1, that is what is beta j, the backward probability of being in j at t plus 1, because you have gone from I to j, and the summation of lambda mt and beta mt, which is nothing but the probability of all the n sequences for all the states. Now, probability of being in state I can be given as j equal to 1 to n, the probability of t and I comma j going from probability of going from I to j. So, now we can compute the new estimates of the model parameters. So, the pi of I is equal to lambda I of 1 at time 1, what is the probability of being in I. Then the transition probability I comma j is given as the summation of t, that is all the observations at each time, what is the probability of going from I to j from time t equal to 1 to t, the summation of that is a probability, and divided by the probability of being in that state at time t. Just review the probabilities once more. So, state probability being in that state given the observation, transition probability going from state I to state j given the thing, probability of state I given observation from 0 t plus 1 to t. Okay. So, that is what we are trying to do here, and the emission probability is given that t is equal to, at t you find OT is equal to k, that is the probability of emitting k at time at from state I is that at t the observation is k, and at time t the probability of being in state I given this observation sequence divided by the observation, the complete observation sequence complete state sequence from t is equal to 1 to t, the complete one. So, now with this values you can compute the new parameters. Okay. Now, we will talk about the expectation maximization algorithm. We have already seen before about the forward backward algorithm when we in the previous module when we were discussing both Baum-Welch and Viterbi. Now, actually forward backward algorithm is an instance of a more general algorithm, which is the EM algorithm. Actually, this EM algorithm we have already seen previously for in a general sense. Now, we are looking at how to the EM algorithm has been very intuitively used for finding model parameters of the hidden Markov model. So, that is what we are going to use the expectation maximization for. Actually, what we are trying to say is the forward backward algorithm we used also is actually an expectation maximization algorithm, but it is an instance of the more general type. So, here we, in any expectation maximization algorithm you have two steps, the E step and the M step. So, in very simple terms the E step here is a computation of the forward and backward probabilities given the model. So, the model as usual in hidden Markov model, when you say model you have three parameters, the transition probability, the emission probability or the observation probability given a state, and the initial probability, which is the probability that a particular state can act as a can be an initial state. Now, so that is the expectation. So, expectation step we are assuming that a model is given and we compute the forward and backward probabilities. Now, the important step here is the M step. Once you compute the forward and backward probabilities, using those probabilities we are going to re-estimate the model parameters. So, that is what we will be doing. Okay. So, so how do we do this parameter re-estimation? You use the forward backward algorithm, which is a hill climbing problem. Okay. Now, using an initial parameter estimation or instantiation, which is a guess, the forward backward algorithm will iteratively re-estimate these parameters and improve the probability. Now, what has been given to us, the observations. Given observations are generated by these new parameters. So, the probability of that this particular sequence, the observation sequence is generated by this model, that probability is maximized. So, what we will be doing is we will take an initial model, find the backward forward probability and the probability of the observation sequence, and then we will try to change the model parameters such that this observation sequence probability becomes the maximum, improves. Okay. So, that is parameter estimation. So, the three parameters that need to be re-estimated, as we have been talking in the last two modules again and again, the initial state distribution pi of I, which is nothing but the particular state I being an initial state, transition probability, the probability of given a state Si, the probability of going from Si to Sj, and the emission probability, the probability of being in state I and seeing the observation O at time t. So, that is the emission probability. What is the probability? Now, we are going to re-estimate the transition probability. For this we define a probability called eta t of I comma j, where t is the time at which you see this transition occurs and I comma j is the going from I to j. So, what is the probability that now you are associating state, what is the probability that qt, that is you see the state at t and that time you are in Si and you see qt plus 1 or you have the state symbol as qt plus 1 at time sj given the observation sequence and the model parameter, that probability. Okay. So, that is called eta t of I comma j, which is defined as what is the probability of being in state I at time t. Please note we are talking about t and this I mean number of parameters. So, what is the probability of being in state I at time t and going to state j given the current observation, current model and the parameters. Okay. So, that is what we are trying to define this. This is the transition probability when we talk about the learning problem. Now, how do we re-estimate the transition probability is the next question. So, what we do here is the transition, now the previous part is 0 t minus 1, 0 t, 0 t plus 1, 0 t plus 2, because we are going to talk about both the forward probabilities and the backward probabilities. Okay. We are going to talk about both this the forward probabilities and this is the backward probabilities. We are going to talk about both. So, how do we define this eta t of I comma j? This is defined as the forward probability of being in state I at time t, and then the transition probability, that is the probability of being in state t at alpha. Alpha ti is defined as the probability of being in state I at time t, the probability of making a transition from state I to state j, okay, that is aij or the transition probability, then the probability of, okay, emitting bj at time t plus 1. So, that is this, and then you have a beta t plus 1 j. So, the probability of seeing j at time t plus 1 is called beta t plus 1 j. So, you can see this alpha I, alpha ti, beta t plus 1 j, and so that is the what we are trying to see among, okay, the summation of 1 to n, I to n, j to n, that is the all the states alpha t of I, the transition probability from I to j, the emission of jth ot plus 1 simple at the jth state, and the probability for all the states, okay, all the states I, the I states we are talking at t and the jth state we are talking at t plus 1. So, we are taking I is equal to 1 to n, all the states in the tth time period and all the states in the jth time period, and we are going to calculate for everything. So, that is what is called the transition probability, re-estimating. So, the intuition behind this re-estimating the transition probability is that the expected number of transitions from Si to Sj and the expected number of transition from state Si. So, what we are trying to do here is we are estimating the transition as now we have in the previous slide we have found out Et. Now, we are just look at the previous slide, we have just found out this. Now, what we are trying to do is we are trying to find out what our job is to find the transition probability from I to j. So, what we are trying to do here is for every t is equal to 1 to t minus 1, try to find out that eta t I comma j. So, what is the probability of going from I to j in the tth state for all the 1 to t minus 1 states, and then do this for t is equal to 1 to t minus 1, j dash equal to 1 to n, eta t of I minus I comma j dash. So, expected number of transitions from state Si to Sj is given by the numerator, and the expected number of transition from state I to any of the j's, that is what it means, for any of the j's for any of the t's, for all the t's for all the j's is given by the denominator. So, in the initial stages we go from I to a particular j, here we are trying to find out for all the j's. So, that gives me the transition probability. So, now we have re-estimated the transition probability using the backward probability, I mean the forward probability, the transition probability that we have guessed, the emission probability that we used initial guess, and the backward probability. So, using these terms we have found out eta t I comma j, and using eta t I comma j for one j and all the j's we have found out the transition, a new value of the transition probability. So, that is what we have done here. Now we can define eta t of I is equal to j to n eta t of I comma j. So, as the probability of being in state I given the complete observation 0, because what do we do when we want to see the complete observation? We have to go from one state to the other. So, we can say that that particular a comma j is not. So, this is we have just redefined that particular expected number of transitions from state Si as given by eta t, and with that we have replaced that that summation part of that with, actually we are just naming it that way. It is actually the same equation as the previous one, except that we call this term as eta t of I mean gamma t of I. So, that is what we got. This is the transition probability. So, basically what we are doing is we are trying to find the transition probability of going from I to S among all the transitions that can happen from I, that I to J from all the transitions that can happen, that is what we get as transition probability. Now, we also have to re-estimate the initial state probabilities. So, the initial state probability pi of I is the probability that Si is a start state. So, what do we do here? We have to re-estimate expected number of times Si is at time, it is at Si at time 1. So, that is defined as pi of I is equal to lambda 1 of I, that is what is the value that gamma 1 of I, gamma 1 of I is this. So, here we just take for one time because we want it to be at the initial. So, just take it 1 and then see what happens. So, that will give you this value. So, initial now we have re-estimated the transition probability and the initial probability. So, similarly we can re-estimate the emission probability also. So, the general idea here is start by devising a noisy channel, any model, for example corpus observation if it is a text mining problem, it could be any hidden structure like tags and passes. So, initially you guess the parameters of the model, you can have an educated guess or random also can work, only the time taken for convergence will be higher. So, what you do is you have two steps in the expectation maximization algorithm. Use the current parameters and the observations to reconstruct the hidden structure. Use that hidden structure to re-estimate the parameters. So, here the current parameters of the model and the observation are used to reconstruct the hidden structure, and then that hidden structure is used for re-estimating the parameters of the model. So, you keep doing this until you reach convergence. This is the general idea of a expectation maximization framework. So, let us assume that you have an initial guess, you have guessed at the unknown parameters, it could be probabilities. Using that you are trying to find the unknown hidden structure, it could be tags. What is observed are the words of the words of the sentence in the case of pass tagging. So, that is given. Given that you can do the M step, that is you are trying to use these parameters to re-estimate the probabilities. So, for example, this is initially given and with the initial guess you are doing this. Then what you do is with the new value you re-estimate the value of the distribution, go back and then you again do and keep doing this till the value no longer changes. So, basically what you are doing is you are assuming some transition probabilities, calculating, in our sense we are calculating the forward, backward, all the probabilities required, and then using that with some understanding to find the transition probability, initial probability and emission probability. So, before we go, let us just look a little bit at, we will come back to the learning model, but before that actually the hidden Markov model is used for finding the tag sequence given a word sequence. Let us assume that n is the number of words and tags. So, you are given, say the man ate the mango. So, you want, that is the word sequence, the man ate the mangoes, the man ate the mango. So, 5, n is equal to 5. You want determiner noun, verb determiner noun. So, that is the tag sequence you want. So, you want to find a tag sequence that maximizes this probability so you can have different tag sequences given the same word sequence. You will choose the tag sequence this maximizes the value of probability. So, that is what you do. So, here that is basically, if you want, if you are talking about a tagging problem, image tagging problem, you could talk of any application that you want. You are given the observation, you want to find the best tag sequence. Normally this is used for a sequence problem, music maybe, pictures, videos. This is typical application, speech. These are applications where HMM has been very commonly used because we are talking about sequence. So, given a sequence of words, you want to find what is the given the sequence of signals, you want to find the sequence of tags. Given the sequence of audio features, you want to find the sequence of characters or whatever. So, that is what you want to model. So, the hat here means that we have chosen the sequence that maximizes, or we have estimated to be the best one, and the argument max says that choose an x such that the function or the probability is maximized. Okay. So, this equation is guaranteed to give us the best tag, but how to make it operational, how do we compute this value? So, intuition of Bayes classification again. So, we are just bringing that part here. So, you use Bayes rule to transform into a set of other probabilities that are easier to compute. So, what you do here is, so this is an argument max. What we are trying to tell here is, actually we want to find, given the word sequence, we want to find the tag sequence, but this can be rewritten using the Bayesian equation, where you are asked to find the posterior probability. You can replace the posterior probability by the likelihood and the prior probability. Now, the word sequence never changes. So, the tag sequence, you could choose different tag sequences. So, given a tag sequence, what is the word sequence? That is the likelihood, and given the probability of the tag sequence, which is the prior, and the denominator is the probability of that, this denominator is the probability of the word sequence, that never changes. So, what you do is, you try to find a tag sequence that maximizes the likelihood into prior instead of the posterior directly. So, this is this part where you want to find the given the tag sequence, what is this word sequence, that is called as likelihood, and what is the tag, what is that particular sequence of tags coming that together as a sequence is called prior. And now comes our assumption that the probability of the tag sequence given the word sequence, probability of the word sequence given the tag sequence can be approximated to, given the tag, what is the word. Okay. And the probability of the tag sequence can be the likelihood can be approximated like this, and for each and every word and tag. So, instead of taking it as a sequence, you can take it word by word. So, for example, what is the probability of given determiner, what is the probability of the word, given noun, what is the probability of the word, each and every, all the words there. Similarly, you can find out given the previous tag, what is the probability of the next tag. So, that is the probability of the prior. So, now what happens, our initial problem, given the word sequence, what is the best tag sequence, can be approximated to finding the tag sequence such that given the tag, what is the word, given the previous tag, what is this tag, product of that will give you the argument max. So, we have sort of simplified the problem with a set of likelihoods and prior in addition to some assumptions. Now, that is how we can use hidden Markov model to solve a decoding problem. Now, let us come back to the learning problem. Now, learning problem, normally we already said that we cannot use annotated, it is not very costly to use. So, you can use a plain text corpus and a lexicon. What is the lexicon used for? Again we are talking about past tagging. How can you use a lexicon? You can use a lexicon to say that a particular word, these are the type of tags it can have. For example, I normally use the word can, C-A-N, can. It can be a noun, it can be a verb, it can be an auxiliary verb. So, with that information and the plain text corpus, without any already tagged corpus, you can find the transition and emission probability by applying the diagram. You start with an initial module, then you compute the probability of each state sequence given this current model. Use this probabilistic tagging to produce probabilistic counts for all the parameters using that Bayes theorem and so on, and use these probabilistic counts to estimate a revised model. So, change the parameters, and then which will increase the likelihood that that observed output W is there in each iteration. So, you repeat until convergence. Please note that no label training is required, you just initialize by the lexicon constraints, because otherwise you will have a large set of tags. So, what is the possible tag for each word can be constrained by using lexicon constraints. So, you choose the initial model and you repeat until results do not improve. You compute the values of the probabilities based on the current model using forward and backward algorithms to compute both the transition probability and the emission probability with expectation for counts, and compute the new model. Output likelihood is guaranteed to increase in each iterations, but might converge to a local maximum, that will happen. So, what we have discussed here, we have explained the concept of the model learning in HMM. We have discussed a very interesting completely unsupervised parameter estimation for using the expectation maximization technique for HMM. Remember, for the first two problems that we discussed in the previous module, we assumed that the complete initial probability matrix, the transition matrix and the emission matrix is given to you. Here we are not making any assumptions. You can start with a random or some educated guess, and you can keep on re-estimating the parameters of the model using the observation sequence. So, you can try to find a model that best explains the observation sequence. So, this is with this we have completed supervised, most of the supervised and unsupervised techniques, and looked at some interesting machine learning techniques. Now, we are going to look at a completely different paradigm which is called reinforcement learning in the next module. Thank you.